Thanks.
Yeah, Sirlane is, as I say, the one who has created a C library that's complete for 16-bit posits with ES equal to 1, and it runs plus, minus, times, divide, and the quire. And we're beginning to use that for real experiments. It's patterned after Berkeley soft float, so she's made it, as she calls it, soft posit. And she's one of the many people who has really had to wrestle with every one of the little rules to make things work right and things like rounding. So what I wanted here for a panel was people who have gotten their hands dirty and really gotten into this and figured out what does it take to do this kind of arithmetic. Because I have a number of questions that have been in my mind for a long time that I wish I had a good panel to ask. Just as an example, a detail type question. Should we really allow hardware to have a range of values of ES sizes for every one of the precision sizes? So in other words, a 16-bit would have an ES value of 0, 1, 2, 3, and same thing all the way up to 64 bits. There's arguments for it and against it. And I've had hardware people tell me, oh yeah, sure, we can do that. I've had hardware people tell me, you're crazy, aren't you? That's insane. You can't possibly do that. They'll be very expensive. So thoughts from the panel on just that question, for example? Do we have a microphone? Yeah. Did I already stump them? I hope not.
Then I'll start.
Okay.
So personally, you know that I'm 61 person.
Yeah.
But I would say I would like to see all ES values supported in spite of what I have been doing, because I really think that there are algorithms that can take advantage of this. But to put it like that, switching ES is a bit more complicated in implementation than what most people think. It's unlike just increasing the number of bits. If you keep your ES value, then you're just padding zeros at the end. But if you do it, if you change your ES value, you really have to do shifting and so on. And this is not as clean as one would have thought.
Well, maybe we should jump ahead to, I'm thinking ahead to language support. Suppose you've got a C data type. Right now we have short, int, long, float, and it's not that bad. What happens if you have 12 different kinds of posits? Let's say 16, 32, 64, 8. And you have 16 kinds. I guess if you have 0, 1, 2, 3 for the exponent values, that's a lot of different number types. So it would run slower in software. I think it would also run slower in hardware, right? So that brings me to the question of what do we standardize on if we don't do that? We have to pick the exponents to go with each size. And this is the hardest thing I've had to decide is, do we match the dynamic range of IEEE? Because they're kind of chaotic looking choices, or do we do something logical like 0, 1, 2, 3 for the E sizes for 8, 16, 32, and 64, which looks logical?
Well, I think it's logical. We tried these MATLAB experiments with the same sizes, and it's really very complicated on software level, and I believe it will be the same on the hardware level. So I think it's way too many data types. We have to figure out just a small subset, which is just the best compromise in my opinion.
Yeah.
Yeah, I mean, from my point of view, we are mainly interested in numerical applications, and so the working horse is 64-bit arithmetic, so classical double precision arithmetic, and maybe there is a right for other data formats for 16-bit or whatever in some special applications, but that's not really my business. I don't want to say that it is, so you have different applications also, so we are coming from different sides also, But for me, probably a 64-bit format is the most important.
Drop and replacement.
So I think in my experience, with the experiments that I've been running, I've been seeing that as you increase ES, you're actually getting closer and closer to IEEE, right?
Yeah.
And at some point, it doesn't really pay off anymore, too. So I think
because you lose accuracy.
Yeah.
Every more additional bit of ES is one less bit of fraction.
Yeah, so I think what I've seen is that once you get to E is equals 3, then you're close enough to IEEE that you're not really seeing any benefits anymore.
Yeah. So there's an interesting idea which we really haven't tried, which is set ES equal to 3 for all sizes. If you even have an 8-bit number with ES equals 3, it has a pretty awesome dynamic range. And then all you have to do is add bits to the end to give it finally more, to change it from an 8-bit to a 16-bit posits. You just pad it with zeros. So that's rather appealing. And I hope I'm not going down the completely wrong path by changing the ES value for each of the different precisions. I don't know if anyone's done any experiments with that, but I understand what the IEEE committee went through when they were trying to make these decisions. And I have the luxury of not being in a committee, but kind of dictatorial here for a while. That's going to change. And it's starting to change right now as I'm getting arguments and feedback. And I took a lot of that in the first year where people did not like the way I defined not a number. And I think I've made up my mind now that plus or minus infinity is going to also serve as not a number, which means if you take the reciprocal of plus or minus infinity, you don't get 0. It's got to be sticky. It's got to stay at nan so that you're warned at the end of the program you did something like that. Everybody agrees. I was the only one who wanted to go back to 0. I thought that was cool. But I've been beaten down for that. So that's the kind of questions we have to face.
Can I ask a provocative question?
Please.
So many people have actually been trying and saying that ES equals to 0 is actually the best combination. Just removes E. And we have seen certain results that actually shows that ES equals to 0.
Until you run out of dynamic
Yeah, it's
range,
better
yeah.
because you get more fractions. So I really don't know. I did not run enough experiments to really justify that. But the few that we did run shows that. So I don't know what's everyone's view on that. I mean, it simplified logic a lot.
It certainly does, and I think that we've seen in some of the experiments that we've been running that at some point you simply run out of dynamic range and you actually lose a lot of accuracy by doing that. We saw that particularly in eigenvalue computations where, going with 0 is just not quite enough. But I mean, that's going to vary from application to application, but that's what we've seen.
We may have to go through an ugly period in which, for about a year, we run all kinds of applications, get all kinds of feedback, and finally establish, okay, this seems to be the right ES value, because right now, without all the experiments, I'm not sure we know enough. How do we get languages like C to support posits, valids, and quires as data types that are part of the C standard or part of the C plus standard, plus standard? Because if we have that, then we're in. Otherwise, we're just probably a fake float. That's what's going to happen. This is what you use. It looks like a double. This is what you use. It looks like a float, and that will never make use of the quire, for example.
So at Livermore, we have a tool called ROSE that does source-to-source translation. Mm-hmm. You can actually analyze C code and other languages as well and output code. So it could actually do this automatically for you. It would probably be fairly straightforward to set something like that up.
Okay, but then the quire doesn't act like any other existing data type. It's like a big fat fixed point number, and that's not a standard C type at all, so that there's nothing to translate from, or to. Is there?
Well, I don't know all that much about how the quire is supposed to work, but I was thinking that was part of sort of the hardware register that actually does that for you, right? It's not a separate type. Is that not the case?
Lines of code. Copy this to the quire, add this to it, and then a few lines later say, oh, I'm going to add also this to it, and it'll be part of the code flow. And then finally I'm ready to take it out and round it back to a posit because I'm done with it. That way you can keep multiple sums going, let's say, throughout your code where it's not just a dot product. You don't necessarily want to clump your dot products all into one very compact piece of code, but run an accumulator, you see, and not have to worry about the associative law or rounding error in the accumulator. So I would really like to see a language supported. I don't want to introduce yet another language. This is already hard enough. Does anybody here have a seat on the C committee that sets the standards? Or know somebody who's on the C committee standards and how these things are done? Because it would be great to actually have that kind of effect on on the computing environment. We are boiling the ocean here. Now, we're changing hardware, we're changing software, we're changing applications. Every layer is affected by this. It's almost overwhelming to know where to start, but I know the languages are going to have to change. They don't support what we've got right now.
But is it easier just to create a dialect for now?
Is what?
A dialect. That way you don't have to go through ISO.
Dialect.
Yes, something like GCC. GCC has got extensions. They never
Yeah.
went through ISO, and somehow some compilers support those extensions.
Yeah. Or LLVM. Yeah.
I don't think you want to go through ISO and all the whole process.
Yeah, I know what you
And
mean.
the standard that comes out, you have to pay for the document.
Okay, I like your approach. I think that might work. That's sort of what we're going to talk about that after this panel. When do we have to? We're going to talk about how we plan to set up the consortium and get people's input and organize it and manage it. It's sort of a pre-constitution, if you will. We haven't actually done that, but that's going to be, I think, as you say, not an IEEE standard committee or anything like that. It's going to be a community effort, an open source community effort with some rules. It's not a complete chaos, but it's also not a dictatorship.
A dialect that is supported by most of the community will end up as a de facto standard.
Mm-hmm.
And somewhere down the line, it might become a standard by default.
I think that probably is the right approach. So I'm glad we talked about this, because if enough people are using something, it becomes a de facto standard. Right? Okay. Another thing I'm wondering about is, should there be levels of POSIT compliance, where we say this is POSIT level 1, POSIT level 2, and that allows people to say, well, I've got plus minus times, oh, I've got the choir, and so on. I'm seeing Arthur shaking his head, so somebody run him a microphone.
No, I personally think, there should be one golden truth, and everyone should adhere to it. I don't know who will set that golden truth, but there should be one deterministic way of, don't add more confusion to everything.
Yeah.
Yeah. What I can easily imagine is that maybe some people do everything in hardware, some do some of it in hardware and some in software. So I think you do want to allow for that, but I completely agree that at the end, POSIT compliance should be called POSIT compliant.
Right.
Because people's heads
Yes.
are going to hurt, already anyway. So you don't want to, you don't want to multiply that.
Yeah. The panel want to weigh in on that?
No, I totally agree with that. It should be compliant. Yeah, it should be standardized in a crystal clear way.
Well, that was easy. Is there anybody who doesn't think
Yeah.
that it should be
Yeah.
that it should be just one level, and this is what you have to be POSIT compliant?
Yeah, and if you can have a validation suite, like you just mentioned,
Yes.
right? So having an IEEE standard or something, that's one thing. But just having a clear stamp of approval, right? So people know, okay, if I have something that I think it's this, if I run this, then I can get the stamp of approval. I don't have to negotiate with people. I just have to pass this thing.
Yes.
I think that will get you a long way towards, a de facto standard.
The Singapore people, I think, are hoping that Singapore becomes a hub of the certification. So this is a service that actually might make some money for A-Star, is that we could say, yes, this has passed all of our tests. It's like an underwriter's laboratory for a number system. And we've tested exhaustively enough, as well as looked at the proofs, that it looks good. I've got a very geeky question. Should shift be a standard choir operation? Is it cheap? Is it useful? Yeah, I'm looking at Garrett because he's thought about exact dot products longer than any of us. What, 1978? So,
Yeah, I mean, the exact dot product, you're right. I've been working on this for now nearly 50 years or so. So I think it's an important operation, the exact dot product, the choir. At first we had some different implementations. We used these different algorithms. but the algorithm which we saw here, using kind of long fixed point register, these are probably the most efficient or widespread versions. There are software versions around, for example, quite a couple of software versions by Siegfried Rump, a colleague from Hamburg, and he always wants to underline that he is content with IEEE arithmetic. He doesn't need anything else but IEEE operations, and he can implement kind of quire, maybe not quite as efficiently or not quite as elegantly as a hardware implementation, but at any rate it can be done. So, of course, maybe it's also a political question if you have the power and the backing to fight through standard and special hardware and implementations and so on. So that maybe also depends on the resonance from industry and whatever.
Okay. Well, you didn't face a problem that I face, which is that really large numbers have less precision. So let's suppose you're accumulating and it's getting bigger and bigger. You really want to keep all the precision that you've got way up there in those high bits as you return it to a posit form. And so that doesn't affect IEEE floats at all because they're just flat precision. But maybe I have to add the ability to round the quire after scaling by 2 to the k. Something like that, so as to make sure that I don't lose all those accuracy bits that I went to such a hard time to get. But I'm looking at what does it take to build hardware to shift a 512-bit number, and people are going to do it in blocks. It's not going to be pretty, right, guys? Looking at my hardware people out there.
If you do it once at the end of a long dot product, I wouldn't worry about it. I was going to say, if you do it once at the end of a long dot product, I wouldn't worry about it.
Can it be done in 1 clock cycle?
Well, why is that important?
For speed?
No, I mean, I think this stuff is. I guess that is a matter of debate. But a quire register is, it's hidden state, right? So if I do, so for example, as a computer architect, if I do a long dot product operation and something happens in the middle someplace, and then probably I will just start over again, right? Because otherwise I have to make hidden architectural state visible, and you really don't want to do that. So I think this stuff is, one of the reasons there may be an opportunity is I think we have to, because we are running out of ways to get more efficiency, we probably have to go for longer vector and matrix kind of operations soon in processors anyway, to get the next level of runway, and then intersect that also with the fact that deposits seem to look good for AI stuff. That's probably where your opportunity is. But I don't know. I might be wrong, but that's how I look at it.
He really should have been up here on stage. We got a couple of hardware experts, and a lot of my questions are about how we do that. How do I avoid what happened to IEEE 754? Oh, we got another comment?
Yeah, I think it could be possible with the barrel shifter.
Yes.
So if you look at shift operation, in VLSI side, each it can be shifted using a mux. A mux in a hardware, I would say a single transistor. It could be possible with that a single transistor. Most books say about, well, you can design a mux 2 or 6 transistor. I don't think so. It can be done with a single, with a FinFET.
Yeah.
It is possible.
That's a shift by 1 or a shift by n.
Yeah, it is possible for 1 cycle.
I think barrel shifters are order log n in their time complexity, but they take up a lot of space. So it's a tough decision as to whether it's worth it or not. And that's where my hardware expertise runs out, and where I seek the counsel of people like the ones in this room. I was going to ask the question of how do we avoid what happened to IEEE 754? I mean, you've seen, just looking at the standard, what a mess it is. Does every standard go down this road? Does it always get ruined by corrupt influences and complications and too many cooks? Or is there a way to do a new arithmetic standard in such a way that it never becomes corrupted? I'm interested in your thoughts on that, because that's really what we're here for.
It's like a political question, less regulation, that's it.
I don't think that's what corrupted the IEEE 754 standard.
They introduced too many exceptions.
Well, maybe I should tell you what some of the things that happened in IEEE 754, but I know one thing is industry took control of that early on. IBM and Intel were very influential in things like the 80-bit temporary data type that some processors were allowed to have, but others didn't have to have. So Intel saw that as a way they could have an advantage over their competition. And so they right away wrote in that you don't have to get the same answer every time, because they wanted their answers to be better. And that meant, of course, that we're still today, this day, we get different answers depending on whether the 80-bit register is being used temporarily or not. It's invisible. It's, like you said, the architectural state should never be exposed to the user, but they run the same program twice and they get different answers 5 seconds apart because somebody interrupted the program and the 80-bit register got rolled out to a temporary 64-bit, got clipped down to 0, maybe it underflowed, and now it's not the same number anymore, just because somebody else used the machine for a second. Anyway, this is what keeps me up at night. Maybe I should let the panel bring up anything they want to bring up as a controversial question, if there's something that bothers you guys.
Well, it would be interesting to see what would be the most promising application of posits. You mentioned yesterday machine learning, you mentioned artificial intelligence. I'm a big fan of trying this in three-dimensional computer graphics because there are some applications I'm envisioning that would be extremely promising from the from the viewpoint of posit arithmetic.
We're supposed to go to 540.
So we've been talking about compliance, John. So how onerous is it to actually implement all math functions exactly?
Yeah, that's another thing I haven't talked about yet, but there's going to be 2 levels of math functions. One of them is every input, the result is rounded correctly. If you call something a cosine, it has to give you the correctly rounded result for every input. That is not true for the MKL, the Intel Math Kernel Library. It'll say, oh, it's good to within 2 ops or something like that, units in the last place. That's where you get incompatibilities. That's why you get different answers on different machines, is they have different views of how good does the math library have to be. The IEEE standard got it right when they said plus, minus, times, divide have to be rounded correctly. Before that, a lot of people did not round, even multiply correctly. There were exceptions. So that helped get us consistent answers. But they were not willing to bite the bullet and say logarithms have to be correct for every single input operand. I have discovered, at least in my early work, I can get every single number to be rounded correctly for 16-bit posits. And it's kind of a fun exercise. And the code's only this long. It fits easily on one page. But I have to have the quire. That's what I'm saying. If I don't have the quire, I can't evaluate these things so that they round correctly to the last bit. Because there are these things, it's called the table maker's dilemma, where an exponential value shoots just right through the middle between 2 posits, or 2 floating point numbers, and you don't know whether it goes down or up. It's so close. It could be like 1 part in 2 to the 50th, and you've got to figure that out. But it's very easy just to know where those are and steer around them, make sure that it's biased and gets rounded the right way. So your polynomial approximation isn't as accurate as possible. It's intentionally inaccurate near those places so that it goes through the minefield and picks up all those tricky points. So I know it can be done, and the POSIT standard I hope to issue will say, here are reference versions that are exact. And maybe they're not the best, not the fastest. Maybe you've got some clever hardware you can use. Maybe you can use table lookup. But here's at least something that will get you started that works just with plus, minus, times, divide, and the quire. In fact, I'm trying not to use divide. It just makes plus, minus, times, and the quire. But then people will say, well, those are slow. Look, you've got 50 operations per point. I need a really fast e to the x for my deep learning. So we need another level. And I'm thinking of calling them something like fast approximate unum extension, FAUX, faux. So I have faux cosine and faux log, and it will be a different name. You will never mix it up with the correct one, and it will be good to some number of bits, and you'll have a polynomial or some other algorithm that defines how to do that, and it'll be fast, and it'll be identical across systems. So if you're going to go fast, you have to use this approximation and call it a name that everybody uses, and then we'll have a fast and approximate, but then we'll also have the one that's good to the last bit. And either way, we still get bit repeatability. If it becomes a part of the standard library for an approximate level, and then maybe we need more than one approximate level. Don't know. But what I don't look forward to is creating that math library for 8 bits with ES equals 0, ES equal to 1, ES equal to 2. Every single one of the polynomials is different. Every time you change either the size of the operand or the number of ES bits. That's 16 different math libraries I've got to write. I hope to have a team soon to help me with this, or an extended virtual team worldwide. But that's probably the biggest barrier right now to being plug and play, because you're seeing this hardware that just works, and you just drop it in and it does posits instead of floats. But hey, you've got a lot of things. I think you've seen this. Peter's seen this in his test codes. He's using things like Hydro 2D, Euler 2D, and the shock hydrodynamics code. They don't have any fancy functions in them. They don't even have square roots, right?
They do, but nothing really much fancier than that. I think there's a power in there somewhere.
How did you do it with posits?
Well, we're using the IEEE implementation, which is quite interesting in that these functions are not depending on what precision you use.
You use the
Those functions you
IEEE
get-
thing, so you turn it into an IEEE number, do the function, then bring it back into a posit.
That's right.
That,
And you get different answers depending on what precision you actually call that function at.
I see.
So it's quite...
That's how you're getting by. Yeah, for a while we can live with that, just early on. All right. Any other comments on this whole conference? Because we're going to transition to something very different in a second. Comments about anything you've heard today from the audience or from the panel?
John,
Yes.
about these translation functions, I think, do you have any specific thing in mind for range reduction algorithm for sine, cosine, and tan? Because in different machine you get a different answer because of the range reduction algorithm for different machines. They are different.
Range reduction has to be perfect.
Yeah,
And
so
it's
what's your
ugly.
comments on that?
Range reduction is not bad for logarithm and e to the x. It's a pretty straightforward thing because you've already got the power of 2. And then when you multiply by a constant to turn it into natural log or log base 10, if you do it right, you can correct for those errors that you get as a result of doing that.
So in other words, the algorithm is the same as a floating point?
Yeah. When I did the logarithm, I started with the log base 2 because that's easiest, the argument reduction. You've already got the log. You've got the exponent out there. That's an approximate log. Then you just have to figure out what the log of the fraction is and add it correctly. But then from one log, you can go to any other log, and I was able to derive log base e and log base 10 with not a single rounding error.
Oh, okay. Right.
If anybody particularly wants these right now, I can show you them, but they're only for 16.1.
So may I ask which paper or which author you referred for?
I've been writing math libraries for 35 years.
Okay.
In assembler, mostly. So I've been through all of this. The sine, there are a couple kinds of trig functions. There's like sine, cosine, tangent, but there's also sine pi, cosine pi, and tangent pi, where the pi has been, sine pi is sine of pi times x. So if you take the sine pi of 1/2, you get exactly 1. You don't get a number that's pretty close to the sine of pi over 2 as approximated on your machine. It gets rid of an awful lot of the problems, and it runs about 40% faster than having to do the argument reduction with a big, long, exact expression of pi. We can take this offline. I didn't expect to go into that rat hole. Well, thank our panel, I think, and we'll go on to the next stage.